Namaskar, welcome back. So, in last lecture, we stopped discussing at the point where we were discussing about the paleomagnetism and geodynamo, and then how geodynamo is related to the plate motion and convection currents and all that. Okay. Now, slowly we'll move towards uh, the main part of this course, and then slowly we'll start with the historical seismicity, that is the earthquake. Why we want to consider, because this course itself is like earthquake geology and a tool for seismic hazard assessment. So final data which has been generated or from this type of studies, how they are useful for the seismic hazard assessment, and what were the basis for uh, creating the microzonation map. Okay, but what we have, the zonation map of India based is not microzonation; it is macrozonation. So we have 4 zones. So that also part we will discuss. So zone 2 to zone 5. So fifth zone is the most vulnerable region in terms of the earthquakes. So they are prone to earthquakes and all that. So how this was been arrived, and what is the significance of the to have the understanding and knowing the historical records and considering the ongoing seismic activity, that is what we call modern seismicity. So slowly we'll move and see that what are the ways in which this type of studies can be conducted, and then again how this data can be extracted and can be used for the zonation part, and also this information is important when we are talking about the building codes and all that. So, broadly, if you take the Indian subcontinent, or we have been talking in terms of the plates. Okay, so Indian plate and the Eurasian plate. Okay, so what it has been seen and observed, and this is based on the absolute measurements, but the GPS measurements, where the Indian plate is been kept like it is moving, and the Eurasian plate is like fixed sort of. Then the velocity has been calculated, that in at what velocity the Indian plate is moving towards the Eurasian plate or the Asian plate, you can say, or you can say Tibetan plate. Okay, but mostly we use Eurasian plate and Tibetan plate. Now this, the point to the south here is your Bangalore or Bangalore, and then you are talking about the G based on the GPS. It is around 50 millimeter per year. So the Indian plate moves at the velocity of 50 millimeter per year in a north northeast direction. So this is uh, the direction what it is having, in which it is moving. And of course we have discussed about the initially there was a subduction, then there was a collision and all that, and that what we see the topography here. So you have the Himalayas. Okay, now how from this 55 or 40 50 millimeter or 45 to 50 millimeter per year, it moves. Okay, uh, till the boundary of what we say the Himalayan foothills. It has it has been observed that this is the around, it consumes around 5 millimeter. So if we say that, okay, 50 millimeter is the velocity, and then out of this 50, or the convergence rate, we also talk in that term, and then 5 millimeter is been consumed by your Indian plate from the boundary of the foothills. So left out is 45 around. Now from that 45 across the Himalaya, if you see around 20 to 22 millimeter, okay, it varies of course, but it is not the same all along the arc what we have here. It varies in some millimeter, okay, 3 to 4 millimeter varies, okay. But oh, I mean, in a broader sense, it consumes almost like 20 millimeter per year. Now, if we add this to, okay, for the Indian plate, then we say that, okay, fine, this is around 25 millimeter per year. So this has been taken up by the Indian plate and the Himalayan region. Okay. Now, where the rest of the 25 millimeter is going, so that what most of the scientists they suggest that 50 millimeter out after left out is 25 millimeter is been consumed by various faults which are sitting here. Okay, and then in Tibetan side, or you can say, so there are multiple faults which are consuming faults. We will discuss about the faults and all that. They are the weak zones, and along which the energy, if stored, can be released in sudden form and can create earthquakes. Okay, this is one very important point which we should keep in the beginning in our mind, that okay, fine, that out of 50, 5 only has been consumed by your uh, Indian plate till your the margin of the, or the plate margin, we can say, because this marks the plate margin. This plate margin between the Indian plate and the Eurasian plate. Now, the important part here is that based on the consumption of this 20 millimeter and 5 millimeter, the energy is getting stored because it is getting compressed. The all material, the crust is getting compressed. So, and at after some threshold limit, it will break, and that breaking and sudden release of the energy is your earthquake. So, point here is that if you have larger con convergence, or maybe the consumption of this velocity in the area, so more strain is developed over here. Okay. More strain is developed over across the Himalaya, and that is one of the reason that Himalayan zone is been termed as one of the most seismically active zone on this planet. So this 20 millimeter is resulting into the this accumulation of the strain, and that finally, when it is released, that energy has been released, it results into your major and great earthquakes. Okay, whereas the rest of the area is also consuming, and that the strain is also developing there, and that is the testimony again what we can say, that the earthquakes which have occurred in this region, like Bhuj earthquake in Kutch, Latur earthquake, they are the testimony to this consumption of 5 millimeter. Anyway, this region, or the area between your Himalayan front and the rest, is been termed as low strain region, and this area is your high strain. So this also you should, I think, remember. Now let's see further about this. Okay, so this is what is a model uh, which was been given by Wilhelm, and what he suggested was that not only the Himalayan zone what we have. Okay, so this is the plate boundary you are having, and then you have the Himalayas over here, and this is Indo-Gangetic plain you are having. Okay, so he suggested that not only the Himalayan region is deforming and resulting into earthquakes, but the rest of the plate is also flexing up. Okay. So this is the rest of the plate which is also flexing up, and that has resulted into the Latur earthquake here, the Bhuj earthquake, okay, and then there was the Jabalpur earthquake, there is a Udaipur earthquake. Okay. So there were many earthquakes which have also been experienced in the rest of the portion of the Indian plate. Okay. So it is not that the only Himalaya is active, but Himalaya is the most active. Okay. because the convergence rate we can say is almost like 20 millimeter in that area. So this is an high strain area, that one. Now, as we were discussing about this, that we the historical data, if you consider, uh, so many scientific group they have taken into consideration uh, the information recorded during that point of time. Uh, so that has been taken into consideration to have an understanding that what was the area which got affected by this earthquakes. Okay, so there were like in 16th century, for example, there are a couple of earthquakes like 1505 is there. Then there is another in Kashmir 1555 is there. Okay, so this were the earthquakes in 16th century, which resulted into the vast uh, devastation, or maybe the larger areas were been affected. Then based on the, because at that point of time we never had the instruments, okay, to have the seismic or earthquake measurements and all that. So whatever has been available in the written text, based on that, how far the area got affected and how many people reported that the houses were damaged and all that. So those things were been extracted, and a basic understanding was created, and that okay, what should be the intensity of the ground shaking uh, uh, would have remained at that point of time. Okay, so similarly, there are few more earthquakes, which also, like if you see here, it goes up to this is 25 AD earthquake. Okay. So historical text helped to some extent to have an understanding that there were earthquakes in the past in Himalaya, and major earthquakes and large earthquakes, okay, large magnitude, and great earthquakes we say above around 8.5 or so. So that helped in such some way to have an understanding that okay, this area is active area and this has a potential to trigger large and great magnitude earthquakes. Okay, so even in 19th century, you have couple of earthquakes like 1883, 1803 earthquake, and then in 20th century, if we take, then we had three major earthquakes. One was of 1905 Kangra earthquake, then another one was 1934 Bihar, Nepal, and if you go further this side is Assam, that was 1950 earthquake. Okay, so of course this area has triggered many earthquakes in many centuries also, but then also we still want to have an understanding of the prehistoric earthquakes. Okay, and the question always remains that whether the seismicity what we are able to extract from the historical records are complete, the data is complete or not. So that is another question. So the studies what we are going to discuss about the technique and all that helps us in identifying the prehistoric earthquakes and as well as the historic earthquakes. Okay, so now based on this the macrosic zonation map was been prepared. I'll come to that also. Okay, but the final map, I'll come to that final map. But before, let's see the what was the history of this seismic zonation map, how it started. So this is basically it started in 1962, where we had like almost like 6 zones. Okay, so the A1 was the edition which, so Indian seismic zonation map. Okay, so and this because we had in 19th century, we had 20th century, sorry, we had three earthquakes, three major earthquakes. So in 1962, it was like with one, two, like it's with almost six. Okay, we have, and then again this is more or less similar what we see here. Okay, But later on, as and when the data started coming in, and as and when we experienced the earthquakes and the intensity which was been assigned to that area particularly, because this zoning basically talks about the the intensity or what will be the ground shaking and all that. So red zones, okay, wherever you see this one, they are definitely the areas which will have very high ground acceleration. So seismic shaking, when earthquake comes, the seismic shaking is very high. Okay. Now, if you see in the first map, okay, Andaman Nicobar was not been included, okay, but later slowly it came into picture, and then you see in the sea map 1984, this was been included, okay, because there was an earthquake in 1941 or so. So they were like this again was very important. Again, we had like 5 zones, okay. So this was in 1984. We had from 1 to 5. Zone 6 was been removed actually, because okay, so instead of zone 6 putting in like higher vulnerable zone, or the areas which will experience higher intensity, where was been removed. So 1 to 5, and then those few of the zones were been merged, which you can see here, okay. These zones were been merged. Then there was an earthquake like in 2001, okay, and that was your 2001 was Bhuj earthquake. So the intensity which was been observed, experienced during 2001 was totally different than what it would have been experienced as per the zonation map of 1984. So again, uh, the scientists and the our organizations, they felt that this has to be like updated. Okay. So zone 1, which was like with the least seismic shaking regions, was removed. So finally, we are having 4 zones. So 4 zones are there, that is from 2 to 5. Zone 1 has been removed. Okay. So this is the present status of based on the seismicity. And again, if you see that what we were looking at, this one, okay, this red portion, this one here, this comes from your, this is 1555, okay, this is 1905, this one is 1934, and this side goes is your 1950. So this is based on that. Okay. Again, this part we had earthquakes in 1819, which was recorded by Britishers at that time, and then we had 2001. Now, in between this period, there was another one, 1956. So again, this region was been categorized in zone 5. So at present, what you see is something like before. So this is before 2001, and this is after 2000, and that is your 2002 map. Okay. So where you have this zones. Okay. So zone 1 has been removed. This one has been removed. Okay. And some modification has been done in the zoning part and the contours. But now we are having zone 4 zones only. Okay. So if you see this region, of course, is in zone 5, and this portion here, of course, it falls in the area of not in, it is in Burma, so it is not been shown, but this region is also in zone 5 according to what recent earthquake of Myanmar was along this fault, Sagain fault. Okay. So this is zone 5 here, this is zone 5, this is zone 5, zone 5. Now the question always remains that, uh, which I also keep asking, that what is happening in between here? And of course, we have left out this portion also. This is adjoining area because this is the foothill zone. This is marks the foothill zone. So this is in zone 4. But what is happening in between this? Why this can't be in zone 5 actually? Okay. Anyway, that we will have discussion later on also. But at present, what you see in terms of the seismic zonation map, so we have 4 zones, zone 2 to zone 5. Okay. And and before that we had almost 5 zones. Zone 1 has been removed. Okay. Now there are many uh, major fault lines which exist within the Indian plate also. Okay. And that could be related to, as we were talking about in one of the lecture of uh, uh, plate tectonics, that there are scientific uh, a group of scientists, they suggest that probably there were like multiple small microplates which joined and all that. Okay, because the deformation pattern of each area is different. Okay, that what we call the Harvard trend. There is a trend of the like you are your alignment of the mountain chain and all that. Okay, and then we have Aravali trend, Delhi Aravali, Satpura trend, then we have Eastern Ghat trends and so on. Okay. So they believe that there are the zones and that can result into. But earlier it was been considered that this all stable areas and nothing is going to happen here because it is cratonic area and all that. But now people are like trying to take into consideration. For example, this is the CITZ, okay, Central Indian Tectonic Zone. So this area is basically the Narmada zone lineament you are having. Okay. Anyway, what the context here was that you have like this area was been considered as an like one of the stable region. Okay. So now coming to the historical seismicity and all that. Okay. So if you start from here, just keep that in mind that the portion here what we were talking about, this has been considered because this is a craton region. Okay. And this area is like in like was considered as an most stable because of the hard rocks and all that. Okay, but as we have discussed, this region is already in zone 5. Okay, and this region is also having potential of triggering earthquake. So let us see a few examples from this, that if this was been considered as a stable region, then this is 1993 actually. Okay, this earthquake, the Latur earthquake was there. There was another earthquake in Koina. Of course, Koina has been considered as an like reservoir induced seismic like seismicity. Reservoir in the earthquake was been resulted because of the Koina reservoir, the loading of the Koina reservoir and water in that. But weak zone was there actually. Okay, and that got triggered. Okay. But so that means that it has potential of triggering earthquake. There was another earthquake in Bharuch uh, in South Gujarat, 1970 earthquake. Then there was another earthquake in Jabalpur, 1997. So the point is that the area which was been earlier considered as a stable region is not so stable. It has hosted earthquakes in the past, and it has also shown us that there are these areas can trigger earthquake like in 1993 and 1967 and Jabalpur 1997. Okay. So we'll discuss more about on this part and then move towards that what is the importance of historical seismicity in the next lecture. Till then, thank you so much. Namaskar.